Hello, my name is Jillian Lee. Today I will be guiding you through an experiment in which I observed the motion of an object drop from rest at a certain height. I then created a computational model which predicts the motion of the falling object using Newton's second law and accounting for the involved forces. The computational model initially will only take into account the weight force. We will then create another computational model that takes into account weight force and turbulent drag force. Finally, we will compare the two computational models to the experimental model and determine. Through this experiment, I found that the computational model was more accurate at predicting position of the falling object when weight force and turbulent drag force was incorporated. We will then predict the motion in our computational model using Newton's second law, which is given as force equals mass times acceleration. Newton's second law can then be used to determine the final velocity and the position of the object. These equations are given. As stated earlier, we're going to create two computational models. But why do we need to create two computational models? Why do we need to take into account drag force and weight force? Because force is a crucial part of Newton's second law. The total force in this experiment, F net, is equal to weight force and drag force. Both are at play in this experiment. We expect that when only weight force is accounted for in the computational model, the model will overpredict model position. Once the drag force is introduced into the computational model, the experimental model and computational model will match better because the drag force will slow the object down. The drag force, F drag, is given by the formula B times V squared times unit vector, where B is the drag coefficient constant which varies in each setting, and V is the magnitude of the vector velocity. Drag force opposes the motion of the falling object, and it points in the positive y direction. The weight force is given by mass times gravity times unit vector. It follows the motion of the falling object in the negative y direction. Now, let's look at the setup of my experimental design. In my experiment, I dropped a 0.04 meter diameter ping pong ball weighing 0.0027 kilograms, and I captured the frames from when it fell from above my head to the floor. The diameter of the ball, 0.04 meters, was used to calibrate tracker. The origin of the axes were set at the middle of the ping pong ball, and I oriented the axes so that the ball fell in the negative y direction to make things easier. My time scale was from 0 to 0.567 seconds. The time interval between each step was 0.033 seconds. Let's point out potential sources of error at this time. First, there is difficulty in marking the position of the ball frame by frame. It's difficult to see the ball, for example, in these frames here, where the ball is impossible to see as it moves past my shirt. It blends in. I have to guess where the ball is for a couple frames, which may not be accurate. In tracker, there's also movement in the X position, while we're only expecting movement in the Y position. This may be due to how the ball was dropped initially. It may not. Let's look at the experimental results now. This is the computational model without turbulent drag force. Here, we can see that the turbulent drag force does not seem to be an issue at the beginning, and Newton's second law matches pretty well. However, as time goes on and the velocity begins to increase, the computational model and experimental model differ more and more. Let's look at the computational model with turbulent drag force. When we add in turbulent drag force, our experimental model and computational model match up pretty closely. There's some deviation in the middle of the graph, probably due to errors in finding position in tracker and a spin on the ball. The last half of the graph matches very well. We set the constant B equal to 0.00022 kilograms per meters. This was found through trial and error in order to match the final position. Therefore, we can expect the drag force to at least match the last point of the experimental model, but we have even more matches than just the last point, so therefore we can say we have an overall more accurate model. This final graph plots both of the computational models that we did, with the drag force and no drag force, and the experimental values all on the same graph. And as you can see, the model introducing drag is a much more accurate representation of terminal velocity is when the velocity of a falling object has zero acceleration due to zero net force. The drag force is equal to the downward force of gravity. Because there is no acceleration, during each time interval, the system falls the same distance. Can we use one of our computational models to predict this motion? We can only use the model utilizing drag force to model terminal velocity. Drag force must be incorporated into the model because without it, the system would accelerate at 9.8 meters per second. I looked at the position data of the y-axis to determine if my model reached terminal velocity. If I reach terminal velocity, then there should be equal changes in distance between the data points, but this is not the case for me. Perhaps if I dropped the ball from a higher position, the ball would have time to reach terminal velocity. Now let's imagine a scenario where the object was initially thrown downward instead of just dropped. This would mean our initial force would not be equal to zero. If we throw the ball downward, we may predict that the terminal velocity would be reached faster than anticipated. We can use one of our computational models to see if this is correct by changing the code to have an initial non-zero force. I did 0, 25, 0. This is what our model looks like with a non-zero net force. Looking at the difference between data points, we also see at the end here they are relatively equal, indicating that we reached terminal velocity in a shorter amount of time. Thus, this concludes my presentation.